Hi there, everyone. So here is our second video in this unit. And the purpose of this video is to kind of show you all how ideas about conservation of energy that we've been talking about in our last unit is actually connected with waves and how you see conservation of energy in waves. So the essential question here is, how does the principle of conservation of energy impact observations about waves? So generally speaking, you can think of wave energy as its amplitude. So an object or a wave that has a high amplitude is going to create an image that you see on the top half of your screen. And so the higher the amplitude, the higher that height between that equilibrium and the top of the crest. A low amplitude, you can see the big difference. It's that the height from that equilibrium, let's say, to the crest is not going to be as high. So wave energy is that idea. It's the same thing as amplitude. It's the height of that wave. When we talk about conservation of energy in waves, we're looking at really how high the waves are in that sense. Like if you look at these images, is that height conserved? If you look, let's say, at the high amplitude one, if you look at the amplitude from the first crest all the way to the last one in that wave, is that height conserved or not? High amplitude, again, means high energy. It takes a lot of energy to create that high jiggle, to create that wave. Now, down below, I wrote amplitude is an independent variable. So here's the thing. It does not depend on any of the other variables. It's simply a measure of the energy carried by that wave pulse. So it's not dependent on any of the other variables. All right, here's a little thought experiment for you guys. So let's try and think a little bit about this situation and see kind of what would truly come about with, I guess, yeah, let's just do this. So so let's say you're holding one end of a long rope, okay? You create a wave crest with an amplitude of 0.5 meters. So what that means is you jiggle that rope to create a wave crest that has that amplitude of 0.5 meters. And so that's maybe about 1.5 feet at one end of that rope. So the person, let's say, at the other end of the rope is going to be holding that rope. And so they're going to receive that crest. But my question for you, and I know the star is already up here, so y'all know, but think about it. Would they receive the same amplitude? Would it be more? Would it be less? And the idea here is it would actually be less. And it would end up being lower because the wave itself is going to have a little bit of that amplitude wasted away. And so there's three main ways we notice energy being conserved or not conserved in a system. And so that's something that I definitely want to kind of discuss a little bit in this video for you guys. So let's kind of look a little bit about wave energy over distance, okay? So waves that move through a material are normally are in open systems. And so that total energy is not going to be conserved, just like that last example. So look here, friction between the molecules of that medium, things that you can't see. We can't see molecules with the naked eye. But here's what happens. So that friction between the molecules of that medium, they transform wave energy to that thermal waste energy. And this is something called damping. So that's where the energy actually went. And so damping is this idea. It's what happens when there's actually rubbing between those molecules in that medium. That's what I was talking about. And so as a wave is trying to get through that rope from that last example, here's what happens. You don't see this, but it has to stretch the little pieces of rope against each other And then during this time, they rub and create that little bit of thermal energy, that heat. And that's what you lose. And so if you look at this image here, if this was a wave, like a graphical representation of this rope or wave, let's say, that's why this amplitude, it started off at that 0.1, like that dash mark of 1, pretty high. And then if you notice, the amplitude dissipates away. That energy, that wave energy, is a victim of damping. So damping in general is an example of an open system, because that total energy is not conserved. Now, an example of this, let's say you're yelling at someone. They sound louder the closer you obviously are. So the sound wave is making heat as it goes through the room or the air or whatever, and it stretches those air molecules out. And so again, it's that same idea here. There's going to be a little bit of that thermal energy that's wasted away. Now, some materials will dampen waves a lot, and some materials not so much. All right. Okay, so damping in the real world. These are things that, again, you would experience normally in your everyday life. So again, some materials dampen waves a lot quicker than other materials. And depending on the situation, that could be a good or bad thing. So how well the materials you use, will dampen the wave. Sometimes you want it to dampen it a lot. Sometimes you want it a little. So it depends on the materials that you're using. Now, an example up in the top left in that image, those are panels up on the top of that concert hall. It's not just there for like an artistic representation of some sort. The job of that is to actually reflect or bounce the sound waves off without dampening them. And so what's happening, the sound waves are bouncing off without taking energy or sound from them, like in that last example. Now, the point of this is you want everyone in that room, all the way in the back, to be able to hear the music well. Or else, what's the point of going to a live concert? So those panels up on the top actually allow for a decrease in damping. Now, excuse me. The next example, is, let's say the drummer's on the bottom, the drummer and the sleeper on the bottom. So what if you live next door to this obnoxious drummer? So obviously you're going to want to create an increase in damping. You want the sound to be dampened very quickly so that energy is lost and you don't hear those sound waves as easily. So that person on the left with those drums probably needs to create a soundproof room. And that actually is what would be a good example of that damping. Now, the last example on the right that looks like a gigantic box next to a desk with some computer screens on it is actually, it's a scanning electron microscope. And so this is a very powerful yet sensitive microscope. It's in a lot of research facilities, and you can get some extremely close-up shots of objects down to the atoms that create it. And so the problem with this is, though, if you're zooming in that close, you have to be very careful that this microscope does not jiggle at all, because you won't be able to get the object in focus. So if the if the microscope jiggles, you can't see what you're trying to look at. And so what happens is around these microscopes, cages are created to dampen out all the sound vibrations. Even a car or something that's driving a block away, the vibrations from that car could actually mess with this microscope. And so what they do is they try and dampen out that sound vibration to lower that energy that's coming through. All right, so this next one, this is another way that we can discuss waves, and this is an example, with interference. This is an example of a closed system. Now, I say that, but we all know that there's no true closed system in our world. Everything's really an open system. Now, the idea here is that let's read the question out. It says, what do you think would happen if a 3-meter tall wave, that's about 10 feet, moving to the left through a rope collided with a 2-meter tall wave moving to the right? And so I give this example to kids a lot of times in drawings too, and I say, look at the math of it. Just use your common sense. Well, if this is what's happening, the top part, or the top option A, is correct. When they meet, those the heights of those waves will combine, or those waves combine for that moment in time, and a 5-meter tall wave is actually created. If a material doesn't dampen much, we see this property known as interference. And so that's what this example, or these next few examples, will be about. It's about interference. Now, let me give you some examples of this. So because of conservation of energy, what we've been talking about, the amplitude of the two waves actually add up, or actually subtract, when they meet in the middle. And I'll give you some examples of both of these in a little bit. And there's two types of interference. One's called constructive interference. The other one's called destructive interference. And so, constructive interference is when two wave crests on the same side of the material or medium meet, they end up combining. Now, here's the important thing. The waves are not bouncing off of each other. It looks like that in this top left image, but that's actually not what's happening. What ends up happening is this wave on the left side will combine, and then it'll keep going to the right. And so waves in these examples are not changing direction. They're going to keep going in the direction they do. Now, let's see, what else did I want to make sure I explained in here? Oh, destructive interference. I felt like I was forgetting some of these things. Okay, destructive interference. I don't want you to think about the word destroy, because their wave is not being destroyed, okay? The wave pulse is on the opposite side of the medium. And so here's what that really looks like. Let this image, or this start over again. Here's one on the bottom, that's a trough, and the one on the top was a crest. And so that's what I mean, where the wave pulses on each side, so one on the left, one on the right. That pulse starts on opposite sides. One's above the equilibrium with a crest, one's a trough. And so what happens here is when they pass through, when they come towards each other, like right here, like what ends up happening is, you can kind of think of it as the waves are canceling out, but that's not truly what's happening. In a sense, they subtract from one another. And so what happens is, once they go through and meet, that interference occurs right, it's going to move slowly, there. What'll happen is the waves will then continue to move in the direction they were going. And the waves basically regenerate and pass through each other. All right, this next piece, a little bit more about interference here. So this is a good way for you to be able to see what interference looks like in a drawing. So because of conservation of energy, the amplitude of these two waves will add up when they meet in the middle. And so this one on the left side, actually, I'll start with the right side because we started with constructive. So constructive interference, if you notice the wave pulse, and I'm going to keep using like two people, one on the left side, one on the right side, creating holding a rope. And so the person on this left side creates one pulse in the upward direction to create this crest. And then the person on the right does the exact same thing, but in the opposite direction. So if you notice, both of these are crests. When they interfere with one another in part B right here, they combine, they add up. But then this wave here is going to keep going to the right. And so watch my mouse. This wave at the bottom, when they keep going, will end up over here. Okay, and then this one will end up over here. So that's an example, like a graphical representation of constructive interference. Now, destructive interference, a little bit different. So instead of there being, like let's use the same example this time. Let's say we have a rope, we have two people on each end. One person's pulse is in the upward direction to create a crest. And then this person on the right side is going to do the opposite and create that pulse in the downward direction. And so when they start coming towards each other like this, what's going to happen is when they interfere right on top of each other, because this amplitude and this amplitude of the initial pulses are exactly the same but opposite, they completely cancel out here. They basically subtract each other, or one subtracts from the other. But the waves keep moving. They don't just stop right there. And so this wave that we started on the left side will keep going towards the right. And then the one on the bottom, again, they all regenerate, will go towards the left. And so I know part of the bottom is actually covered up. So let's wait till that little thing disappears. There we go. And so at the end, the bottom part of that, you see everything is inverted in a sense. All right, we are almost there. So a couple other things we'll talk about. We'll talk about boundaries and reflections. And so when a wave hits a boundary of one medium to another, some things generally happen. And so when, the wave energy actually splits up into 3 or more smaller pieces. So an example of this could be light, rainbows, music, like sound waves. And so when waves hit that boundary or get to the end of one medium, there are 3 things that could happen. One could be that the wave, and we'll talk about sound waves specifically, can be absorbed by that medium, basically like completely absorbed by it. Some of that part of that wave can be transmitted, basically going through the medium. And then part of that wave is reflected. Basically, it bounces off back into the original medium. And so here's an example with this image that I can show you. Let's say someone is playing music outside in their backyard. Let's say that's the sound right here. This sound wave is coming through, and then this is your wall in your house, okay? Some of that sound wave is going to bounce right off. That's being reflected. Some of it will actually, the sound wave will be absorbed by the wall. Some of it will actually go through, which is why you hear noises outside when you're inside and all your doors and everything are closed. Let's see. In this example, energy is definitely conserved. Even though it's split up, it's definitely conserved because energy in this situation is not necessarily lost. Let's see, there is a little bit of damping, which does occur, but the wave energy still exists. It's just now in a different form, okay? Let's see. All right. An example here that I have, just put some values to this, okay? So let's say we have like the total energy is conserved, and then like the amplitude of every piece has to be less than that original wave. And so here's a good simple example. Let's say we made an original wave that has 10 joules of energy, okay? And what happens is we can say that 5 joules of that would be transmitted. It'll go straight through. Some of it would be reflected, 4 joules of it. And then 1 joule of it would be absorbed. If you do 5 plus 4 plus 1, that's 10. But what ends up happening is it may split up, it may look different, but it's all still there. All right, we are done. So to summarize, go visit that essential question again. How does the principle of conservation of energy impact observations about waves? And we are done. Have fun.